Hello everyone, welcome back to Diksha Karnataka YouTube channel, and today is another episode of Decode NCERT, and I am going to discuss a very important chapter, that is moving charges and magnetism. So if you are joining this series for the first time, so I request you open your NCERT book, visit this chapter and follow with me. And if you are already following it from the start, then obviously you know the drill, that you have to open your NCERT when you are following this series. So without any delay, let me start with the series. Okay, so first is the chapter is moving charges and magnetism, and we will start with the introduction. So in the introduction part, one important point to remember, this is somewhat important in my opinion, that one objective questions might come from this line. What is that? Oersted concluded that moving charges or current produce magnetic field in its surrounding space. So which of the following can produce magnetic field in its surrounding space? A static charge, a current, only moving charges, both moving charges and current. So you have to answer both moving charges and current can produce a magnetic field in its surrounding space. And it was Hans Christian Oersted. He is the first one who did this experiment and proved that. Some detail about his experiment and his life story is also given here. You can read that if you are interested in that. Okay, but as far as one more important thing is that we are basically dealing with three-dimensional things, and while drawing them we are only using a paper. So sometimes it's very difficult for us to draw objects. So that's why there is a special symbol that we use, is that a dot. A dot is basically something is used by into the paper. Okay, emerging out of the paper. So anything emerging out of the paper is basically denoted by dot, and anything going into the paper is denoted by a cross. So what is the meaning of that? Suppose I have some current or some field or whatever it is. Okay, if that is coming out of the paper, if it is coming out of the paper, then we denote it is using a dot and then a circle. Okay, that means it is coming out of the paper. Anything that is going into the paper, that is denoted by this symbol. Okay, I hope you are familiar with it and you are used to these symbols, but it is sometimes confusing. So how to remember? Cross is into the paper and dot is out of the paper. So one way I remember is that cross is basically, you can consider this to be a target practice. Okay, it is like a target practice board, the dart board. You take a dart and you throw it towards the cross mark, right? So that is how you are throwing it. So throwing it means through this cross mark it is going into the paper. Okay, and whatever opposite of that, it is out of the paper. That's how I try to remember. Even I sometimes get confused if you give me some lot of diagrams with dots and crosses. So it is very confusing for sometimes. Okay, cross is into the paper, dot is out of the paper. So if you are someone like me who is confused about dot and cross, you can find your own way, that what is the meaning of out of the paper, what is the meaning of into the paper. I remember this cross one. Okay, if you throw a dart, that is the target of it, this cross point is the target. So you want to hit that point, that means you are basically going into the paper. Okay, so we will see that in this application, and I hope you have seen this kind of diagrams in especially electromagnetic induction chapter, where a lot of this kind of dot and crosses are used, right? So based on this, the direction etc. are important in because most of the quantities that we are dealing with are vector quantities. So that's why this is one of the important starting point, not in terms of exam or anything, but only for basic understanding of the overall subject. Now, source and field magnetic force. So this is very, very important, that when you have a electric charge kept in an electric field, it experiences a force. Okay, and we have studied this equation 3-4 times now. Okay, F is equal to Q into E. If you remember, F is equal to Q into E, this equation, this formula we have studied again. E is basically given by Q r cap by 4 pi epsilon naught r square. So you just multiply with this small q to get the electric force. This is called electric force. Okay, this is just a simple reminder of whatever we have done. Just as static charges produce an electric field, the current or moving charges produce an addition to electric field, also magnetic field. So what is the meaning of that? A moving charge has an electric field as well as magnetic field. So if we have already learned in the first introduction that moving charges or current, they can produce magnetic field. But what happens to the electric field? Is it gone? No. Electric field is inherent property of a charge. Okay, whether the charge is moving, whether the charge is static, it does not matter, there will be an electric field due to the charge. But when the charge is moving, an extra field is getting added. That extra field, we are calling it as magnetic field. Okay, even though this chapter talks about magnetic field, the basic ideas of magnetic field, bar magnet, etc., we will study in the next chapter, moving charges and magnetism chapter. But here we have started with only current. So basically this chapter is linking with current with magnetic field. In the next chapter we will discuss about magnetic field. In my opinion, if you want to arrange the chapters better, moving charges and magnetism should have been the first chapter before this chapter. But this is the chapter that is given in NCERT, so I am following the NCERT book. Now, magnetic field and Lorentz force, this is very, very, very important concept, that when a charge is moving in a external electric and magnetic field, when a charge, now what we are saying, a charge is moving in the presence of external electric as well as magnetic. Now external electric and magnetic field both are present. Okay, and charge is also moving, it is not static. So if the charge is only static, it will only interact with the electric field, right? Charge is static charge, it will only interact, it will only ask question to the electric field. Okay, what are you going to do with me? But if the charge is moving, then that charge will ask questions not only to the electric field, it will ask question to the magnetic field as well. What are you going to do with me? So that what is going to happen to the charge, that is been answered by Lorentz. Okay, and that force is called Lorentz force. Lorentz force has two terms. One is electric field terms. This is the force due to the electric field. This is the force due to the magnetic field. QVB. Q V cross B, that is the force due to a magnetic field. Okay, this is F electric plus F magnetic, that is the total force acting on a charge, and this form is very, very important. So they will ask what is Lorentz force and explain the terms. So you have to explain the terms. Q is the charge moving in an presence of electric and magnetic field, then it will experience as a force. That force is given by Lorentz force. This is the thing. Okay, now it depends on Q, V and B, charge, particle velocity and the magnetic field. Force on the negative charge is opposite to that of a positive charge. So if we say, generally we consider this charge to be positive. In case of electric field, it does not matter, because electric field already is only simply multiplication is there, so sign will automatically be included in this. So plus E means in the direction of E, minus E means in the opposite direction of E, right? So plus Q will move in the direction of electric field, negative charge will move in the opposite direction of electric field. So that is simple. For electric field it is not complicated, but for magnetic field it gets complicated because it's a cross product, V cross B. Now which V we have to consider? So basically it depends on the direction of velocity, it depends on the magnitude of charge as well. So generally we consider Q and V both are positive. Okay, Q and V both are positive. B has a direction, right? So based on that, whatever V is there, depending upon the direction of V and B, we can find the direction. Now if the charge is negative, then whatever force V cross B, so suppose this is the direction of V, this is B, so V cross B, suppose this is the direction of force in case of a positive charge, then for a negative charge the force will be in the opposite direction. So this formula, the direction is slightly complicated, but not super complicated. You have to remember that the force on a negative charge is opposite to that of the V cross B. Okay, the magnetic force Q into V cross B included as a vector product of velocity and magnetic field. The vector product makes the force due to the magnetic field vanishes, becomes zero if the velocity and magnetic field are parallel or antiparallel. This is very, very important, that V cross B, so we have a cross product, right? Cross product means cross product can be 0 when sin theta is 0. A cross B is magnitude wise AB sin theta, right? So when two vectors, suppose V and B, they are parallel or anti-parallel, this is the parallel direction, this is the parallel direction, okay, and suppose there is another one who is moving in this direction, then I will say this is the anti-parallel direction. So parallel means in the same direction, anti-parallel means one and other is opposite direction. So suppose we say 1 and 2 are parallel, 3 is anti-parallel, right? So in this case angle is either 90 degree or angle is either 0 degree or 180 degree. So both cases sin theta is 0. So that's why this magnetic force becomes 0. Okay, this is one of the important concept. So if they are perpendicular, the magnetic force is maximum. So generally we have seen in case of work done etc., when they are perpendicular the work done is 0, but in case of magnetic force, work done force is maximum when they are perpendicular. The magnetic force is 0 if charge is not moving, obviously as V is equal to 0, only a moving charge feels the magnetic force. Very, very important. So as I said, F is equal to QVB sin theta n cap. Magnitude wise, most of the cases when you are solving numerical problems, this n cap you can ignore because only magnitude is important. So QVB sin theta. Okay, but when you are writing in exam, for board exam, then force vector is equal to QVB sin theta n cap. But only Lorentz force is important for board. For all other purposes, this QVB sin theta is important. Okay. Dimensionally we have magnetic field is F by QV. The unit is called Tesla. That is very important. The unit of magnetic field is Tesla, named after Nikola Tesla. Tesla is rather large unit. A smaller unit which is non-SI is called Gauss. Okay, Gauss is also, you know, Gauss's theorem, you have learned about Gauss, right? So Gauss is also a scientist, Tesla is also a scientist, and they have different uses of their theorems. So Gauss is another tribute to the famous scientist. So that's why it is said Gauss is non-SI unit. Basically it's a CGS kind of unit, and it is 10 to the power of minus 4 Tesla. 1 Gauss equals to 10 to the power of minus 4 Tesla. Okay. Generally in your exam you can stay relaxed, but if they ask you this question in an objective MCQ, that might possible. But all other competitive exam, they generally give you in Tesla, and they will give you 10 to the power of minus 4 Tesla. Okay, so no need to worry about it. Now, in the presence of an external magnetic field, the force on these carriers are NLA QV Q into VD. Okay, these are just a mathematical treatment of magnetic force on a current carrying conductor. So they have derived the formula. Okay, force is ILB or BIL. I like to remember Bill sin theta. If this formula is written as BIL sin theta, scalar wise. Okay, this is the magnitude of the force. This one you have to remember, Bill sin theta. Okay, based on this formula, lot of questions, lot of numerical questions tend to come. Okay, so this formula you have to remember. Okay, what next? This is the force on a current carrying conductor. So you have to remember that. Next is motion in a magnetic field. Now what is happening? Now the charge is moving in a magnetic field. So what is the meaning of this cross? So meaning of this cross means into the paper or out of the paper. Cross means hit it into the paper, okay, and dot means out of the paper. So as you can see that first consider the case Q into V cross B. V is perpendicular to B. The perpendicular force Q V cross B acts as a centripetal force and produces a circular motion perpendicular to the magnetic field. Okay, so this is the, so when the charge moves in a magnetic field perpendicular direction, it rotates in a circle. Okay, it rotates in a circle, and the radius of the circle you can calculate using this formula. You can this is a very simple, this force, magnetic force, should be providing the required centripetal force. So centripetal force is mv square by r. So after solving, you can calculate r is equal to mv by qv. Okay, and angular frequency and a normal frequency also you can calculate. Omega is angular frequency, frequency is nu. Okay, so that is qb by m. Okay, now if the this is called cyclotron frequency sometimes. Okay, cyclotron frequency sometimes, even though cyclotron is directly not there in your syllabus, but cyclotron frequency can be asked because they have given you the formula for this frequency. This nu is called cyclotron frequency. So that is qb by 2 pi m. Okay, this frequency is basically called cyclotron frequency. This nu is called cyclotron frequency, right? So they might sometimes ask what is the cyclotron frequency. Now so obviously this is helps us to design a cyclotron. Now if they are not perpendicular, okay, if they are not perpendicular, there is some angle between them exists, then it moves in a helical path. Okay, so this is the helical path. Okay, this is shown here. So in the general motion is helical motion, circular motion is a spatial motion. Okay, so as you can see, this is the perpendicular component, this is the parallel component. Along the parallel component it moves ahead. Due to the perpendicular component, it moves in the circular path. Okay, and there is when it is moving in a helical motion, okay, you can calculate the pitch. Pitch means how much distance it travels in 1 second. So time period, if you calculate the time period from the formula, you have calculated frequency, so you know that frequency and time period are inversely proportional. So from there you can directly calculate time period. If you calculate time period, you can calculate, this is called pitch. This formula is important only for your competitive exam. This formula is not important for board exam, but pitch is sometimes asked in competitive exam. They will give you the value of velocity, they will give you an angle, and based on that you have to calculate the pitch. Okay, you can check this solved example. They have solved one example. Now next question is, next part is magnetic field due to a current element, Biot-Savart law. The most important concept from this chapter, one of the most important concept of this chapter. This diagram is just simply a curve. Okay, if they ask you to draw, if they ask you to explain Biot-Savart's law, definitely the diagram is compulsory. Okay, what is I dl? Proportional to current I, proportional to current element IDL, that is also fine. Some student write current element IDL, which is also fine. Or you can directly mention proportional to the length dl, proportional to current I, proportional to the sine of the angle theta. Okay, and inversely proportional to the square of the distance. That is the Biot-Savart law, and it is written by dB is equal to I dl by r square. Now why they have given it r cube here? Why in the book they have given r cube? So these are the small things, they skip it and you get confused when reading the book. Okay, so according to the Biot-Savart's law, and wherever you study Biot-Savart's law, you will notice that it is given in the form like B is basically dB. Actually dB, small element, we are calculating the magnetic field due to a small element, mu naught by 4 pi, this is obviously there. Okay, I dl sine theta by r square. Okay, so this is the formula. This is the scalar formula. But I have seen students, they write r cube here and they come and ask, sir, it is there in my book, please give me full marks, because in my book it is r cube. In your book it is r cube, because what they have done, instead of writing dl sine theta, what they have done, they have written in a vector form, and you did not understand that fact, and what you came here saying that. So if you are writing this r vector, so what you are doing, you are adding one extra r in the numerator. To balance that extra r, what you are doing, you are dividing it with an r. Okay, you are dividing it with one r, right? This is the fact. Or else, how can you avoid that? I should have expected that from NCERT book at least, that instead of writing in terms of r vector, we write r cap and we keep it r square. That way we could have kept the dimensions correct. We could have actually kept the dimensions correct. Okay, so this is one of the other way to represent, but this is a very common represent if you study physics in future. Okay, this type of representation is very common. Whenever there is a vector multiplication, we always use the vector and divide it with one extra magnitude to compensate the magnitude. That's it. Okay, so till there is one thing that I realize about NCERT book is that it is not super optimized. Many teachers wrote this book. Every teacher has their own point of view. Some teachers have simplified it too much. They could have added some extra points, but they have simplified it too much, making the future chapters very difficult to understand, and in some cases the chapter is written very difficult. So if the previous chapters are super simple, then you find difficult to understand at certain level, right? So this is one of the thing. Also, the right hand screw rule, you can find the direction of magnetic field using right hand screw rule. What is right hand screw rule? We will see in a while. Okay, so the magnetic field is given by, this is the scalar form that is we are familiar with, right? The magnitude is mu naught by 4 pi I dl sine theta by r square. So avoid everything, just use this form. If you are writing the scalar vector form, very good, you are most welcome, but otherwise this scalar form is all what is expected from you when you are writing in the exam. So don't fall for the trap, use this form, write this form. Okay, now mu naught is called permeability of free space, and mu naught by 4 pi is equals to 10 to the power of minus 7 Tesla meter per ampere. This is one of the constant, like you have seen epsilon naught. Okay, you have seen in first PU, you have seen gravitational constant G. Similar to that, mu naught is also a constant. Now there is an interesting relationship between epsilon naught and mu naught, that epsilon naught mu naught is equals to 1 by c square. We will see that again in the electromagnetic wave chapter, but for now we should remember that epsilon naught into mu naught is 1 by c square. This is important for competitive exam. This is important for your objective questions. For all purpose, this is a very important relationship. They might give you the values as well. Sometimes they might ask you the what is c. Okay, so everything is important from this formula. Now let's move on. So this is another part, magnetic field on a axis on a circular current loop. So this is a very important derivation. Okay, derivations, you can follow my derivation video. Okay, I have solved it there. You can follow my Brahmastra chapter video. This derivation is done there as well. Okay, the final result is what we are focused on. Derivation, you can follow this derivation. The steps are already mentioned here. Similar steps I have done in Brahmastra and my derivation video. Now B is basically given by bx I cap mu naught I r square divided by 2x square plus r square to the power 3 by 2. So this is the normal general magnetic field due to on the axis, and if you put x equals to 0, you get the magnetic field on the center of the current carrying loop, right? So current carrying loop, this is the current carrying loop. So you can find the magnetic field due to current carrying loop as well. The thumb rule, right hand thumb rule, if you point your thumb in the direction of current and then roll your fingers, that will give you the direction of magnetic field. Okay, so this is one of the formula. Curl the palm of your right hand around the circular wire with the finger pointing in the direction of current. The right hand thumb gives the direction of magnetic field. So you have to curl your direction, curl your fingers in the direction of current flowing in the circular loop, then thumb will give the direction of magnetic field. We will see that in detail in our next chapter as well, north pole, south pole, etc. So magnetic field detail about magnetic field concept is not even given in this chapter. Only it is just a concept that there is a magnetic field and magnetic field is associated with magnet, but magnet introduction is not happened yet. We will do that in the next chapter. Okay, now Ampere's circuital law. This is also very interesting law. It is similar to that of the Gauss's law in electrostatics. What is that? The Ampere's circuital law is very simple. It states that whenever a current is closed by a linear closed line, okay, closed line, linear the current element dl, as much as product added together, we consider the limit as the length of the element. It gets smaller and smaller, the number gets larger, the sum of the tends to integral. Ampere's law states that the integral is equal to mu naught times the total current passing through the surface. So if the surface is bound by a linear contour, then that B dot dl, here dl is a line element. You should remember dl is line element. It is nothing to do with the surface element. This is the line element, and it is equals to mu naught I, right? This is the very interesting part. Now there are few points mentioned about the magnetic field about the loop, so you can check this out, but not super important. Main part is B dot dl is equal to mu naught I, and here they have done the magnetic field due to a straight current carrying wire, which turns out to be mu naught I by 2 pi r. This is the straight current carrying wire. Okay, if you are trying to find the magnetic field at some points P, say at a distance r, then this is the formula. This formula is important. They might ask you to prove it. This proof is very simple. You just need to take a simple Amperian loop. Okay, this is the radius r, and from there you have to, the diagram is not given here, but if you can draw the diagram, it is very helpful. So from there they have done same, magnetic field is constant, so only thing that you have to consider is closed loop of dl. Closed loop of dl is basically the circumference is 2 pi r, so that is equals to mu naught I. So B equals to mu naught I by 2 pi r. Simple derivation. This derivation has applications as well. We will see that. Now I told you that we will explain how to find the direction of magnetic field due to a straight current carrying wire. Here is the law. Grasp the wire in the right hand with your extended thumb. So suppose the current, this is a wire, okay, this is carrying a current in the direction, say this direction. Okay, so what you have to do, you have to grasp your finger such that your thumb points in the direction of the current. So your thumb pointing in the direction of the current. Your fingers will curl around and the direction of the magnetic field. So what is this? If you point your fingers in the direction of magnetic field, then your curled hand will give you the direction of magnetic field. So this is basically what they are trying to say. The magnetic field is circular, first of all, okay, due to a straight wire, and the direction is in this direction. Okay, which direction? In this direction. Okay, this is the direction, so you can find the direction using your right hand and your fingers. Next important concept is solenoid. You can skip the previous part. You can read it once, but not super important. Next important part is solenoid. So as you can see, inside the solenoid, the magnetic field is constant. Okay, except the edges, magnetic field within the solenoid, around the center and most of the region, magnetic field is constant. It excuse me, it varies only at the edges. This is called edge effect. Okay, now magnetic field, you can calculate this constant magnetic field, and this is mu naught Ni. Okay, mu naught is the permeability of the free space, N is the number of turns per unit length, and I is the current. So based on that you can find the magnetic field inside the solenoid. Next is force between two parallel currents, the ampere. So as I said, we will apply that magnetic field due to a straight wire. So that is what we are going to do here. First we will find the magnetic field due to this wire at this wire's location, and then magnetic field due to this wires at this wire's location, and then we will find the force acting on it, and then we can find the definition of ampere. Okay, so the entire derivation, again I have done it in my derivation video. You can check that out. It was done today only, so you can check that video where I have done this derivation in detail. And this is called the magnetic force per unit length between two parallel wires carrying current. Okay, the above expression is used to define ampere. Okay, so what is the definition of ampere? The ampere is the value that a steady current which, when maintained in each of the two very long straight parallel conductors of negligible cross section and placed 1 meter apart in vacuum, would produce the each of the conductor force equal to 2.10 to the power of -7 newtons per meter of length. So this is very, very important definition. Okay, so basically the question comes that find the force between two parallel current carrying wire and hence define Newton, hence define ampere. So that is very, very important. So this is the definition of ampere, and how to define ampere you have to check my derivation video. I will not give you in this video. In this video we are only talking about what is important from your NCERT book, right? So the torque on a rectangular current loop is uniform magnetic field. This is also important. Okay, torque is given by IAB, but this is not the complete formula. Complete formula is when you have n number of turns and then it becomes NIA. Okay, NIA is the magnetic moment. Okay, magnetic moment is NIA, and the torque is given by M cross B. Okay, main in black. So main in black is the torque, and here this M is called the magnetic moment, and the magnetic moment is given by NIA. So magnitude wise the torque is given by NIAB, NIAB. NIAB means precious. So this is one of the formula that also you have to remember. Okay, either you remember these two formulas separately or you can remember this formula. This is a way of remembering what is the meaning of the torque acting on a loop when you kept it in a magnetic field. So loop is current carrying. So what is this happening here? We have a loop. This is a current carrying loop and you kept it in a magnetic field. So when this current carrying loop is kept in this external current carrying field, okay, it experiences a force. Because of this force it experiences a torque. Okay, because it's parallel, both ends are parallel, so one end will experiences a force in the upward side, another will experience in the opposite side. So in turn it will experiences a torque, and that torque will help it to rotate. Okay, this torque will help it to rotate, and that is the basic function of most of our electric motors. Okay, all the electric motors like fan. Okay, fan is one of the example of motors, and there are many other types of motor that work on this principle. Okay, there is an armature coil inside the motor. Okay, and there is a magnet, electromagnet. Instead of using fixed magnet, they use electromagnet. So current is used, and the current is also used to produce the magnetism. So both way, okay, it works perfectly, and our fans, our many other devices work on this principle. Okay, even the motor that pumps the water in the roof, that is also somewhat depend on basic principle is this. Okay, there are some complex mechanism involved in that case, but basic principle is also the same. Now circular current loop as a magnetic dipole. Okay, the magnetic field at large distances due to the current in a circular current loop is very similar in behavior to the electric field of an electric dipole. Okay, so circular current loop, so when the loop is circular, it behaves like a it's similar to that of electric dipole, and we call it a magnetic dipole. Okay, magnetic dipole, magnets are always a dipole. Okay, basically magnets are dipole, but unlike electric dipole, the distance was very, very small, right, between positive and negative. right? So magnetic dipole, that is bar magnet, if you consider, north pole and south pole can be as long as possible. For example, earth, it is also a magnet. Its north pole is almost in the north pole and south pole is almost in the south pole. So there is a difference between magnetic dipole moment and electric dipole moment. Okay, electric dipole moment are always happening between charges which are very, very close to each other. So in that sense, the current carrying loop, that is a circular coil which is carrying current, okay, you can consider this is to be a magnetic dipole. It has a north pole, it has a south pole, and they are also very close to each other. Okay, and that magnetic dipole moment, the formula for which is given by this, M equals to Ia, same formula as above. Okay, if the current is carrying through the loop is I, and if the area of the loop is A, then the magnetic dipole moment is I into A. Same formula as before. Other than that, nothing much is here. Okay, they have done the magnetic field in terms of the dipole moment, which is fine. Okay, the same formula that you have used in the past, same formula they have used. Only thing is they have considered the radius small, so they have approximated this. Okay, this is the approximation they have used here. Not super important, but only for your concept. Okay, you should know that a current carrying loop can behave as a magnetic dipole for objective purposes, obviously. Now this is the formula for moving coil galvanometer. What is galvanometer? So we know that when a current flows in a rectangular coil, okay, it experiences a torque, right? Oh, that's torque formula you have already calculated, NAIAB, right? NAIAB. So that formula is used when this entire thing is fixed on a solid housing, okay, along with some kind of spring system and one pointer. Okay, so based on how much current is flowing in that coil, okay, the pointer can detect it and they will show some value, okay, based on the torque. So this spring is basically balancing the torque to help it to show the current passing through it. Okay, and in 2025 blueprint, the working principle of this was given as a question. So explain the working principle and mechanism for a functioning of a moving coil galvanometer. So you have to write this from this paragraph. I have discussed this in my Brahmastra lecture. You can check it out. Other than that, this is the formula, this is the function on which the deflection, this angle, okay, through which it is deflected, that angle is basically phi. So initially at rest it was at this, right? It was at this, right? At 0. So this is the 0. Suppose, okay, galvanometers generally rest at 0 is middle, but for now assume that the galvanometer rests here. Okay, after some current flowing through this, it deflects by some angle is phi. Okay, this angle phi is basically proportional to the current that is passing through this coil. Okay, so this coil means whatever current is passing in the external circuit, it has an external circuit connected to it. Okay, so this is the deflection and the current relation. Okay, now the galvanometer is a very sensitive device. It gives a full scale deflection for a current of the order of microampere. Okay, for measuring currents, the galvanometer has to become connected in series, and as it has a large resistance, this will change the value of the current in the circuit. So this is very, very important, that when you want to convert a galvanometer into ammeter, you have to consider 2 points. First of all, galvanometer is very sensitive and only a microampere current is sufficient to burn it. Okay, if more than certain microampere current passes through the galvanometer, it will be damaged forever. Also, the internal resistance of the galvanometer is quite high. So you want to measure, suppose you want to measure current in a circuit, okay, and you applied galvanometer directly. First of all, there is a chance that galvanometer will not function. Okay, it will function for once and then it will die. Okay, or another chance is that whatever current you want to measure, you are not able to measure that exact current. What you are measuring is the current after this galvanometer is added. So galvanometer, suppose the resistance was 1 ohm and you added a galvanometer of say 100 ohm. So now the resistance is 101 ohm. So you are only measuring the current due to the galvanometer and not due to the actual 1 ohm resistor. So what to do? So what you have to do, you have to put a parallel resistor with the galvanometer. This is called shunt resistor. Okay, and that shunt resistor, this mathematics also we have done in our class. This part, this shunt resistor helps it to lower its resistance, and this can be used as an ammeter. Now this is called the current sensitivity. So for KCET aspirants, this is a very important formula. You have to remember this formula. Okay, spring constant is K, N, A, B, number of turns, A is area, B is magnetic field. So this is the important formula. What else? Similarly, a galvanometer must be connected in parallel with the circuit. So you have to remember that voltmeter are connected in parallel, ammeters are connected in series. So this is also point of objective question if it is easy question. And this is the voltage sensitivity. Voltage sensitivity is given by NAB K 1 by R. So this is also very important formula. Okay, now there is some relationship given between so what will happen if you are increasing the current sensitivity, what is happening, you are increasing the voltage sensitivity. So you can check this out for KCET purpose. Okay, and we have completed this chapter. Nothing important is given in summary. Summary is good to revise the chapter quickly. Other than that, nothing super important is given, which is only summary specific. So I will complete this chapter now, and I will be back with a new chapter in our next class. Till then, bye.